Welcome to Study Loop.
For the question, here's a diagram that I've already drawn, and I've stated each variable for pressure and volume, as well as the mole count, the ratio, and just that the heat change is 0 from A to B, as it's adiabatic. For part A, as P1 V1 to the power of gamma equals P2 V2 to the power of gamma, then we can apply this to our question and say that P A VA to gamma is equal to PB VB to the power of gamma. So we can rearrange this for the pressure at A, and that is equal to PB VB to the power of gamma divided by the volume at A to the power of gamma. By substitution of the numerical values we have, 1.5 atm times 0.009 meters cubed. This is to the power of the ratio 1.4. And that's all divided by 0.002 meters cubed, again to the power of 1.4. And this gives 12.319 atm. Rounded up, this is 12.32 atm. And this is the same as, by conversion, 124.8324 Pascal. For question B, as dq is equal to n CV dt, and this is for a constant volume, then Q is equal to n CV delta T, so change in temperature. And we know that Cp is equal to Cv plus R, gas constant, and that gamma, the ratio, is equal to Cp divided by Cv. So we can substitute in the second equation into the first, and a bit of rearranging. So Cv is equal to gamma Cp minus R, and then some more algebra. Cv bracket 1 minus gamma, close bracket, is equal to minus R. It's from factorizing. So then we could say that Cv multiplying by a minus is equal to R divided by gamma minus 1. By substituting that back into our equation for the change in heat, and the heat energy is equal to nR delta T divided by gamma minus 1. And we know that PV is equal to nRT. So we can say that the difference in PV over gamma 1 is equal to the heat energy. This is from the ideal gas law. By substituting in our values that we know, so by expanding the delta, PAVA minus PCVC divided by gamma minus 1. And we can substitute in our known numerical values, and this gives an answer of 5,481.68 joules, which rounded up is 5,482 joules. This is dependent on what significant figure you use for the pressure, and some people carry through different values. For where the cycle happens, we know that from A to B, the change in heat is 0, so it can't be there. And we know from B to C is a reduction in temperature and volume, so no heat is added there. Therefore, the cycle happens from C to A. By following the same method we used for B, however, in this case, we have a constant pressure. So Q is now equal to NCP delta T. And then using the same equations again, where Cp is equal to Cv plus R, and we know that the ratio gamma is equal to Cp divided by Cv. By then substituting everything into our equation for heat, Q is equal to gamma times nR delta T divided by gamma minus 1. Again, using the ideal gas law, we can expand on this and say that gamma times PC VC minus PV PB VB divided by gamma minus 1. And substituting in the numerical values that we have, we get minus 3,723.706 joules, and rounded up, this is minus 3,724 joules. Again, there's variance depending on significant figures of your pressure. We know from A to B is delta Q is equal to 0, so there's no heat. It's a constant heat. And we know from part B that heat enters the system from C to A. So this leaves us that heat exiting the system happens at B to C. For part D, we know that the work done, W, divided by the heat entering the system, is equal to 1 plus the heat exiting the system divided by the heat entering the system. So we can rearrange this for W, where W is now equal to QH plus QC. And substituting in the values, 5,482 joules minus 3,724 joules is equal to 1,758 joules. Again, there's variance here depending on where you round up in previous questions. For part E, to find the efficiency, we know that eta is equal to the work done over the heat entering the system, where eta is the efficiency. So the efficiency is equal to 1,758 joules, which we worked out in part D, divided by 5,482 joules. And this gives 0.32, which when times by 100, it gives you 32%.